Excellent. So welcome everybody to this week's One World seminar in machine learning. And it's a great pleasure to have today Bamdad Hosseini from California Institute of Technology. And I've been really looking forward to see this talk. So I'm excited to learn about the recent things happening there in the group at Caltech and your recent work. So yes, Bamdad will tell us today about conditional sampling with monotone GANs. And before we start with the talk, let me just say that, so Bamdad is very happy to take questions also during the talk. So if you have questions, then feel free to just unmute yourself and ask. Alternatively, you can also make use of the chat function and post your questions there, and then we can ask them to the speaker at a convenient time. And so this talk will also be recorded and then will be accessible on the YouTube channel afterwards. So yes, welcome Bamdad, and you have the floor.
Okay, thank you, Franca. Hi, everybody. It's a great pleasure for me to be here. Thanks to the organizers for having me, and also to all of you for being here to listen to my talk. So I'm a postdoc at Caltech. I've been here for a couple of years. We actually worked closely together with Franca. And I generally work in sort of intersection of math and data science and uncertainty quantification. And what I'm talking about today is sort of, interestingly enough, it's kind of connecting all of those areas together. And it's basically the question of how can you do conditional sampling using generative models, okay? So before I say anything mathematical, just to tell you about my collaborators. So some of the stuff I'll talk about today is in this archive preprint. My collaborators, Nikola Kovachki, who's a PhD student at Caltech. A lot of their credit for the nice pictures you see in this talk will go to Nick because he has been doing the numerics for me. Ricardo is a PhD student at MIT working with Yusuf Marzouk, who many of you probably know. He's a professor in aerospace engineering. And again, many of the ideas in the talk are actually things that Yusuf has been working on for a while, and Ricardo is also an expert in this idea of like triangular maps that I'll tell you about in a second. All right, so here's an outline of my talk. I'll start with a sort of a, you know, not expansive, but a little bit longer than you know I like, but you know, a longer introduction to make it clear sort of what the problem we are looking at is, and sort of what the main ideas underlying the work are, and also talk about the literature, because I find it's kind of important. There are a lot of confusing terminologies in the literature that we need to clarify. Then I'll talk about sort of the meat of the mathematics of the method, which is sort of using generative models to do conditional sampling. I'll show you some numerical examples for that. And then in the third part of the talk, this is more experimental stuff, sort of fresh off the oven, some things we've been working on the last couple of weeks, and then I'll show you that. It's just because we got so excited, I wanted to really share it with you. All right, so let's get to the introduction. So there are sort of 4 problems that in my mind appear sort of to be very closely related. And so I'm gonna talk about those. So the first thing is sort of in supervised learning and inverse problems. If you work in any of these fields and you've seen the other one, you kind of feel like, okay, this is pretty much what I've been doing, right? So these 2 fields seem to be very close together. So let's take a closer look at each problem. I apologize if I'm oversimplifying things, but that's just because it's an introduction for now. So in deterministic supervised learning, you have an input X and an output Y. So this is going to be my notation through the talk. And you typically assume there is some ground truth mapping psi dagger so that the output Y is defined as sort of the value of this psi dagger as at X, right? So there's a functional relationship between your input and output. then the goal of supervised learning, at least in the deterministic setting, is that if I give you a new input X star, predict the value of output at the new X star, right? And you typically do this, again, very simplified setting, but you approximate this psi dagger with some other function psi star. So this can be, you know, if you're doing linear regression, for example, it's linear functions, or you know, if you're doing neural networks, this would be a neural network. But the goal really is that the output is going to now be approximated with psi star of X star, right? So let's look at inverse problem. So in the inverse problem sort of literature, the goal is similar, but a little bit different in that you have some unknown parameter now, which would be y, and then you have indirect measurements of this parameter, which is x. So the notation is not standard here. I'm using, you know, typically in inverse problems, y is the data. I'm using this sort of flip notation to be consistent with machine learning. And you have some functional form. So there's some function f dagger of y that gives you x. And then now given a new value of x, you want to approximate the corresponding parameter y. So in a way, you try to invert f dagger, but it's not invertible. So typically you solve some kind of optimization problem. You need to sort of regularize the problem to make it well posed. Okay. So the two problems don't seem like maybe they're kind of related, but not so much. If you employ the probabilistic perspective, it becomes a bit easier to see the connection. So if you do probabilistic supervised learning, you would take your training data, input and output pairs to be drawn from some joint measure nu. And your goal is, given a new X star, identify or sample the conditional of Y on X star. So if you think about supervised learning in this sense, then it becomes very closely related to the Bayesian approach to inverse problems, where again, you have your measurement pairs, right? So measurements X and parameter Y. You put a prior on Y, you pick a likelihood, and then you want to identify the posterior, which is the posterior of Y conditioned on the new data point. This is, again, the conditional of an underlying joint measure, which is given as follows. So this is what I mean by this equation, is that you draw a sample, the measure on X and Y that you get by drawing a sample Y from your prior, and then generating a data X for that sample Y, okay? So they're both conditional sampling. That's the point that I'm trying to make. So now let's take a look at generative models and measure transport. So again, I'm now talking about completely different problems, and then I'll tell you how all of these, in my mind, they're connecting. So what is generative modeling? Again, very simple sort of explanation. I have training data, draws from a measure, doesn't even have to be input-output pairs. And the goal is to generate new samples, let's call them Z star J's, so that they're also distributed according to this measure nu. And the way you typically do this in literature is that you choose a reference measure eta, and then you train a map T so that if you push eta through T, you get the measure nu, which is your target. And you like to do this because if you had such a map, you would just draw samples from your reference, which is presumably an easy thing to do. And then you would just set Z star equals to T of S, right? So you just evaluate T at the reference samples, and you get samples from the target. So this, I mean, the way I'm stating it, it's probably clear if you're familiar with measure transport. This is exactly a measure transport problem, right? So in measure transport, you have eta and nu, two measures, and then you want to find a map T so that you map eta to nu, okay? Or you push eta to nu. So obviously, I mean, this is a huge field. Some notable directions, probably the most famous one is optimal transport. People in image registration have been looking at this as well. And even sort of older than optimal transport in some regards are these triangular transformations, which this paper of Bogachev, it gives a nice overview of that. And this is what we will focus on in this talk, okay? So it's an old mathematical problem, and it's pretty clear why these two are related. So let's, step back for a second. So if you kind of believe the very simple explanations I just gave. So what I'm saying is generative modeling has a nice connection to measure transport. Conditional sampling has a nice connection to supervised learning and inverse problems, but there's a missing link in between these four sort of fields, which is that can you do conditional sampling with measured transport, okay? And it's a highly non-trivial problem, really. It may seem like it's something you should be able to do easily, but it's not actually, it's pretty hard, okay? And that's where sort of this talk is going to fit, is using measured transport ideas for doing conditional sampling. And if we can basically make this a solid line, then we're good to go because we can use generative models to solve supervised learning or inverse problems. All right, so what do I mean by using measured transport for conditioning? So the type of problem we will look at today is the following. So you have a joint measure nu. So this is a probability measure on the input-output space. I'm gonna just employ the supervised learning terminology for convenience. So this calligraphic X and Y from now on will denote the space of input and output. You pick a reference measure on the output on Y, and your goal is to find a map S going from the product of X and Y to Y, such that if you evaluate this map S at a new input X star, right? So if you fix X star, it's now a map from Y to Y. So you can push your reference measure eta of Y through this map S star. And you want to find this map in such a way that the push forward of the reference is precisely the conditional that you want, okay? So the conditioned variable X star here shows up as an input to the map S. And you want this to be true for X star almost everywhere in the support of nu, okay? This should not, at just first sight, there's no reason for this to be true, right? Or even possible. But it turns out that you can actually do this like explicitly. You can actually construct such maps explicitly, and it's something called the North-Rosenblatt map. It's been studied extensively in the literature. It's a pretty old idea. I'll just tell you very briefly the main idea in constructing it, because it can be a pretty, it can be a handful to describe. But this book of Sant'Ambrogio actually has a very nice description of it, so I highly recommend looking at that. So let's concatenate the input and output, and let me just work in finite dimensions. So I'll take X to be in Rm and Y to be in Rn. And the North-Rosenblatt map is a triangular map. And let me also take this opportunity to tell you what I mean by triangular map. I simply mean a map T going from Rm plus n to Rm plus n that has this kind of form, okay? So this should be T2. So it's, the first component is just a function of Z1, the first component of Z. The second one is a function of Z1 and Z2 all the way up to the last one. So if you take the Jacobian of this map with respect to Z, it would be a triangular matrix. So that's why we call it a triangular map. So this North-Rosenblatt map, as I said, you can construct it explicitly. So here's how you do it in R2. And if you understand this, you can do it in any dimension pretty much. Let's say you have your reference and your target. So eta and nu, they have Lebesgue densities H and G. First thing you do is you define the marginals of these densities. So H1 is the marginal, by integrating out Z2, and then G1 is the marginal you get by integrating out Z2 for G. Then you first define T1, the very first component, as the optimal map that pushes H1 to G1. So this you can write down because it's basically the, let's see if I'm gonna get this wrong or not. It's gonna be the CDF of H composed with the inverse CDF of G, okay? Hopefully I got that right, yeah. So this you can write down exactly. And then you do disintegration or conditioning. So you write down the disintegration of H with respect to the Z1 variable. So you fix Z1, you define these new densities, and then you define T2, the second component. Again, these are now densities in 1D, right? So we can, again, map them exactly using their CDF. So you define the second component to be the map that pushes for every fixed Z1 this disintegration of H to the corresponding disintegration of G, okay? And you just keep going forward. And you can already see, because this disintegration, you can essentially think of it as conditioning H and G at Z1. It's not surprising that the North-Rosenblatt map will exactly do that conditioning that we wanted in the previous slide, okay? And if you look at against Sant'Ambrogio, you can see that sort of stated formally. Okay? So you can actually do this problem that I talked about. Okay. All right, and this idea is basically what's underneath the algorithm that I'll present today, which is what we call monotone GANs. So I just wanted to give an overview of it at the beginning of the talk before we get into the nitty-gritty details of the math. So the basic algorithm looks like this. So you take input and output. For now, let me make these finite dimensional again. So Rm and Rn. You have some underlying joint measure nu. You pick your reference to be just the standard Gaussian. So we just pick it to be the Gaussian, the standard normal on Rm plus n. And you take your map T to be a block triangular map. I'll tell you again what I mean by block triangular, but it's basically that it has one component on the top that only depends on X, and then another component at the bottom that depends on both X and Y, but maps into Y. Okay, so this S map is important, as you can tell by my choice of color and notation. What we do is we put neural networks on K, S, and this function and this little f, which will be our discriminator from the, from the generative modeling side. Then you have training set, which is given to you. It draws presumably from this measure nu. You generate a bunch of samples from your reference, which is free pretty much. And then you train the maps K and S by minimizing the GAN loss for the map T. Okay, I'll talk about this a little bit as well. And the important trick is that you need to do this optimization problem with some monotonicity constraints. And I'll show you a theorem that tells you why you need this, but it's actually crucial. And when you have the monotonicity constraint and you solve this optimization problem, the resulting S star map is precisely the map that's going to allow you to do conditioning. Okay, so that's really the sort of the overview of the method. It's basically the usual GAN training, except you need a slightly different parameterization of the map and you need monotonicity constraints. Okay, so let me motivate this a little bit practically. Why would you even want to do conditioning with generative models? So there are
Sorry, can I ask you a quick question?
Mm-hmm.
The F that you had on the previous slide, that's given to you, right? Or you also...
No. So F is a neural network, and then you do a min-max. So F is you're maximizing over F. Yeah.
Okay, okay.
Mm-hmm.
Excuse me, what is the big N, big J here?
Oh, sorry, I should have said that. My bad. So big N would be the number of training points. Big J would be the number of samples you drew from your reference eta.
And you don't suppose, so it's approximation. So you want those to be large enough, right? To have good approximation.
Yes. So I'll show you so this is like an empirical approximation of two integrals, right? So you can tell there's going to be an expectation with respect to nu and an expectation with respect to eta. So the capital N, so that's why, you want N and J to be large, yes.
Okay, thank you.
Yeah. Okay, I'll get into the details of this in a little bit. Yeah. Okay, so practical motivation, again, why would one want to do generative modeling for conditioning, right, for conditional sampling? One thing is it naturally lets you do probabilistic supervised learning and uncertainty quantification because, you can easily compute, statistics on the conditional of Y given a new input X star. The approach that I showed you is actually model agnostic in that it only needs samples from the measure nu and the measure eta. And it does not assume a particular functional relationship between your input and output. And this can be helpful in many settings, for example, cases where you have black box models or cases where you have maybe intractable likelihoods, for example. And the other thing which is kind of nice about the approach I showed you is that we only need to train the map S once, and then we can do conditioning for any new input X star, right? So if I had many new inputs for which I wanted to identify the conditional of Y and sample it, I just need the same map S. I don't need to retrain the map S for any new input. Okay. All right. So let me now go to the sort of do a review of the literature, because as I kind of hinted earlier, it's kind of important to place exactly where our method fits in the literature and sort of clarify what we can do and what we cannot do. So the related rich literature on sort of generative modeling, this is more sort of for people who may not be familiar with the field. There are sort of three big methods that people use. It's generative models, generative adversarial nets, GANs, that many of you have probably heard about. Goes back to around 2014. And the idea is really given, samples from a measure, you want to generate new samples from the same measure. It's presented in this original work as sort of a minimax game sort of approach. I'm coming at this perspective, so optimal transport sort of things, it seems more natural to me. So this paper of Novozin, Sike, and Tomioka has a nice explanation. There's also this famous Wasserstein-Gann paper. And I also put these two reviews here, again, for people who want to get an overview of the field. A very closely related set of methods is also normalizing flows. These are actually pretty much, you can kind of think about them as different discretizations of the North-Rosenblatt map. I'm oversimplifying again, but that would be the sort of the image that will be helpful if you start to look into this literature. It's actually pretty old, by machine learning standards. It goes back to 2010. Youssef has worked on very similar ideas to normalizing flows since at least 2012, if maybe earlier. This is the earliest paper I could find. Again, there are very nice review papers for this field. There's one by Papamakarios et al., and these are the guys at Google. There's one by Kobyzev, Prince, and Brubaker. Also, these are at Borealis AI. I highly recommend reading the papers. They're very approachable for mathematicians. And then another method that's kind of related to what we do, although a little bit more distant, are the variational autoencoders, which are, I guess their main point is trying to find sort of nonlinear dimension reduction, maybe. But regardless of that, they're still trained as sort of mappings of measures. So there's some connection in VAEs to our ideas in this talk as well. So neural networks and inverse problems. I put some references here, again, mandatory sort of inverse problem references if you're maybe someone on the machine learning side who's not familiar with inverse problems. Obviously, it's a very old field. So this book of Vogel has the deterministic approaches to inverse problems. It's a very classic reference, very approachable. Sort of the Bayesian approach, I recommend the Caipio and Somersolo book. It's also pretty classical now. So these are like the classic sort of approaches to inverse problems. Using neural networks in inverse problems is a newer idea. It goes back a couple of years now. A lot of it is being done by Ozan Oktem. Michael Unser has a lot of works in this direction. Carola Schonleb and Rebecca Willett as well. You've probably seen their talks if you're following, for example, the One World Mind seminar. But the sort of approaches that have so far been explored are kind of different from what we do, because some of the approaches basically use neural networks to construct regularizing terms in inverse problems, which is not completely model agnostic. And then there are also other methods that use the neural networks to directly solve an inverse problem. So go from indirect measurements directly to the parameters. For that, I strongly recommend this paper of Gottschling et al., which is on arXiv, where they actually argue that that can be a very, very bad idea, depending on how you're doing things. So one needs to be very careful when one is using neural networks to solve inverse problems directly. Okay, which is not what we're doing, but you know, it's something to be mindful about. And then using generative models for conditioning. So this sort of where our work fits. It's you know, maybe a little bit thinner literature on the machine learning side. There is some confusion in the terminology. There are things like conditional GANs and so on. They're solving very different problems. So conditional GANs is conditional sampling when you, for example, say, I want random images of the number 7. So go generate random number 7s, okay? What we're trying to do is, given some image, I want to know what is the probability of that image being the number 7, okay? So that's different type of conditioning. There's also the work of Adler and Ockham, which I should note, called deep Bayesian inversion, which is actually very close to what we do. But as far as we understand, we couldn't find theoretical support for what's being done there. I might be wrong, so if anybody knows, they can correct me. There's the work of Belghazi et al., where they try to learn all the exponential, you know, exponentially many conditionals of a distribution. It kind of includes what we're trying to do. So if you try to find all the conditionals, but it's going to be intractable for the kinds of problems we're going to look at. And lastly, this new paper of Wang, Lindgren, and Dimakis is actually very interesting. So they look at a slightly different problem where you, given a generative model, you want to compose it with a new sort of flow that allows you to do conditioning. But if my understanding is correct, for each new data, you will have to train your new map again. So what we do, sort of compared to all of these, is that we want to train a single map that characterizes the conditional for any new input X star. Okay, so that's just to clarify what the goal is. All right. So with all of that out of the way, let me now tell you about the mathematics and the method itself. So I mentioned in my overview slide that we're going to use block triangular maps. So what I mean by a map T being block triangular is simply this. So again, from Rm plus n to Rm plus n, I say it's block triangular if the first m components depend only on x1 up to xm, and then the next ones depend on x1 up to xm, and then y1 up to ym. So if I just take the Jacobian of this, it's going to be a block triangular matrix. That's simply it. Okay. And again, just to remind you what the goal is. So the goal is to find this map T in such a way that T is going to map your reference eta to the target. Let's say the target is this banana distribution. Then you want to condition this banana distribution at some point, let's say x1. So let's say the conditional is this blue curve here. And what we want to achieve is that we want to go back to the reference, condition the reference at some point, right? So this is now not at x equals to 1, but at some other point. Because it's a standard Gaussian, it will always be the same, you know, standard Gaussian in 1D. But the goal is to train the map in such a way that S can now push this conditional of the reference to the target conditional, all right? Okay, so how do we do this? We do it by an optimization approach. So we're going to take the map T to be the minimizer of such a cost function. So in sort of abstract sense, you simply need capital D to be a statistical divergence. And by that, I just mean a positive function on the product of probability measures, such that if it's 0 if and only if the measures are the same. Okay, so if I achieve cost 0, then I should be exactly pushing the reference to the target. And I'm putting the dx dys here just to emphasize that t is pushing the joint measures to each other, okay? And we solve this for an appropriate class categorical T of maps from Rm plus n to Rm plus n, okay? So the way you pick the appropriate class, you're probably already wondering, why am I introducing the K here as input? It's basically this theorem, which is actually not too hard to prove, which states the following. So suppose that you have a T star that is a global block triangular minimizer achieving zero cost. So it actually achieves the cost zero. And for simplicity, let's say your reference is the standard Gaussian again. And it has this form, right? So it's K at the top, and then S of K of X and Y, okay? So suppose you have such a map, then if T is surjective, then for any nu X star in the support of nu, by this I mean the marginal of nu and X, it holds true that S star of X star can push your reference marginal to the target conditional that you want. So this theorem is basically telling you that if you have this kind of parameterization of your map, there is no neural networks or anything here. If you have this kind of parameterization and the whole map T is surjective, you're good to go. All you need to do is just extract this map S and you can do the conditioning that you want. So you need to supplement this with existence result, but that's easy to do because block triangular maps, their existence has been known for a long time. It's basically the results that show you the existence of the North-Rosenblatt map. It's very general. You pretty much just need nu and eta not to have atoms. That's pretty much it, okay? Bogachev, if you look at his measure theory book, actually has a proof for like Suslin spaces. So it's very general idea. Okay, so this theory is sort of the foundation of our approach. The question that remains is, what do you do about surjectivity? How do you guarantee surjectivity? So the way we do it here is, using again classic results from nonlinear functional analysis. We employ the Browder-Minty theorem, which basically tells you that a map is surjective if it's continuous, monotone, and coercive. So continuity you can get by your parameterization. Monotonicity you need to impose, which I'll talk about in detail. Coercivity is the one that for now allow me to scrape it under the rug, because it kind of depends on the tail behavior of your map, and in practice it's not so relevant because you will have finite samples. So for now, let's ignore coercivity. Okay, so monotonicity is the important thing. All right, so with that theory in mind, I'm gonna now, skip a whole bunch of steps and just go directly to the discretization, right? So for our divergence, we're going to pick the GAN divergence, which is going to take this form. So you take the supremum over continuous functions, taking value between 0 and 1 of the sum of these two expectations. So if you're a optimal transport person, this should very much remind you of just a dual form of like a Wasserstein distance, right? Except that you just pick F to be a different class. It's not Lipschitz functions. You pick T, calligraphic T, to be strictly monotone block triangular maps. So again, this familiar notation you've seen. We assume we have continuity, and this is the strict monotonicity constraint. And it's for omega, for WW prime eta almost everywhere, okay? And to implement this in practice, I'm gonna put a tilde on my GAN loss, meaning that I'm gonna discretize the expectations just by replacing them with empirical sums. We put neural networks on K, S, and F, as is done in generative models in GANs. And the monotonicity, for now, I'm going to impose average monotonicity by basically asking this constraint to hold, okay? And we will impose it using a Lagrange multiplier, all right? So this is a huge approximation, I know. And I'll show you in a second, well, not a second, in a few minutes, how you can actually do this exactly as well. But this sort of average monotonicity constraint seems to work very well in practice, and it's very convenient to implement, okay? So this is what we're going to do for now. All right, so you might be wondering, sort of, okay, you keep talking about this monotonicity constraint. Is it actually crucial? So here's a 1D example to convince you. So I'm pushing eta, which is a Gaussian, to nu, which is a uniform on -3 and 3. And we kind of train a GAN. We train the monotone GAN, which let me call it just M GAN from now on. And then we can write down the KR map for this exactly as well. So if you just look at the maps, you can tell that the GAN itself is not monotone. So it's not an invertible map. It's not respecting the monotonicity by itself. But the M GAN is actually monotone, and it seems to approximate the KR map, at least, you know. In the tails, you typically have issues, but over the range that it matters, it seems to be doing a good job. And you will not be able to tell there's something wrong with the GAN map if you just look at the samples. So here are histograms of the M GAN and the GAN, and they both sort of have roughly the same quality of samples from nu. So you can't tell that unless you actually look at the map itself. So if you want the map to be invertible, which the theory asks for, you actually need to have monotonicity. Okay, just a mandatory sort of slide about sort of once you have your M GAN, once you've trained it, what can you do with it? I mean, this may be trivial to many of you. You just get a new input X star. You know, you've trained your map, you're done. You extract the S map, you get a new X star. You generate new samples from your reference, and you simply evaluate S star of X star and Y tilde K, which these are your reference samples now. And what you get as output are going to be approximately distributed according to your target conditional, assuming you trained a good map. Okay. All right. So let me now move on to some numerics to maybe convince you guys a bit more that this method actually seems to work. Or I guess to me, it seems like it works well. So here's a simple 1D example. We have 3 functional relationships between input and output. So you have, this is the input, Y is output. So this is nonlinear function of X plus non-Gaussian noise. So the noise is gamma here. In the second problem, we have a nonlinear function of X plus noise, where noise is Gaussian. In the third example, we have multiplicative noise with a nonlinear function of X. The point we're trying to make with these 3 examples is the fact that this approach does not rely on any kind of functional assumption between Y and X, right? You don't need to know what is the distribution of the noise or what the nonlinearity is. So here we use 50,000 training samples. So those are 50,000 pairs of X and Ys. The inputs are drawn from a uniform. We train 3 fully layered networks. They each have a couple hundred parameters in each layer. The details are in our paper. And what I'm showing you in the picture, the first column is the exact joint measures. So these are the PDFs. The second column is the kernel density estimator of the push forward of the full map T. So these sort of visually are matching pretty well. Third column is showing the mean and variances of the output conditioned on different values of input. So the solid line is the mean, and the error bars are the variances, or sorry, standard deviations. If you kind of squint a little bit, you can see the blue curves. So the blue curves are the ground truth values of the means and variances. The red curves are what the MGAN samples are predicting. And then in the third column, I'm showing you some of the conditionals of these measures at sort of 3 values of X star. The solid lines are the true conditional densities. The bars are the MGAN histograms that are doing a good job sort of matching the conditionals. And the funny thing is, when you're doing this MGAN training, you can actually keep track of how monotone the map is, because you can just, you know, you have samples from the reference. You can just look at, okay, how often on these samples am I violating monotonicity? In these 3 examples, we, even with our, you know, hacky sort of average monotonicity constraint, we're getting 92 to 98% monotonicity of the map. So it's most of the time monotone. A slightly more complicated example that I'll come back to in a little bit. The Darcy flow, so this is a PDE. A is the permeability field of subsurface flow, and then P is the pressure of the flow. And for this example, we assume A is piecewise constant. So you have two sets, omega A and omega B, and the value of A on these two sets is capital A and capital B. Your goal is to recover these two variables from measurements of the pressure P. So this is a ill-posed inverse problem because there's a nonlinear relationship between A and P, and there's a lot of smoothing as well. So we take measurements on a uniform grid of 16 points. We have a little bit of noise, and we want to go back to what are the values of A and B. So here, this is an inverse problem. So you need to pick a prior for A and B. We pick uniforms. We discretize the PDE using finite differences. We train the MGAN using 100,000 samples. So for each sample, you have to draw A and B and then solve the PDE. And then I'm going to show you 3 examples where we have 3 data sets, x1 star up to x3 star. These are generated using prescribed values of y, which would be the A and B parameters. And we're going to now compare the MGAN samples with MCMC, which is the gold standard, which we know asymptotically will sample the correct distribution. So you can see that the MGAN kind of matches the MCMC, although in the cases where you get close to the constraints of the prior, it's not doing so well. But if you're away from these constraints, it does a good job. And in this case, we actually tend to get 100% monotonicity for the map. And then the third example, a more complicated example. So we have the MNIST data set, and we're going to do imaging painting. So you have your Y in this case would be the true image. Your X would be the image with the middle 14 by 14 pixels removed. And we train the MGAN on the whole MNIST training set, which is 5,000 images. And then we want to go back and do imaging painting. And this is a case where, there's no prior or anything, like we just have training samples, right? And we also, in the next slide, I'll show you also classification probabilities. For that, we used a pre-trained network. Yeah. So this is the type of result we can get. So the first column are the true images. The second column are the images with the middle pixels removed, okay? And the next 3 columns are 3 samples from the MGAN. So these are generated by the MGAN. And it's kind of interesting because you look at this 9, you remove the middle. So what the MGAN is seeing or basically predicting is that it's getting like, sometimes it's a 7 and sometimes it's a 9, okay? With this 7, if you remove it can be a 4 or a 9 or a 7, right? This first jet-colored column is the mean of the MGAN samples, so you can use it as the predictor of what is the true image. And the next one is the variance of the MGAN samples, which is telling you sort of where most of the variability of the samples are, which is again instructive because, if you think about 7 and 9, they're only different about this little curve at the bottom, and that's also reflected in the variances. And if you look at the classification probabilities, it's pretty interesting because it's saying, okay, this is equally likely to be a 7 and a 9. This one is very likely to be a 4, but it can also be a 7 and a 9, and so on. Okay? And things like 0s and 1 are easy to classify, so you have much lower variances. Again, here we get 94% monotonicity. Okay.
Can you maybe explain one more time what it means for something to be 96% monotone?
Yes.
I don't fully understand this concept.
Yes. So what we mean by this is imagine that you have trained your map, right? You have a map T, and then you want to know how good is it, right? So the easiest way you can verify that is to draw a bunch of new samples from your reference and then evaluate the monotonicity constraint, which is T of W minus T of W prime, inner product with W minus W prime. You can evaluate that on your samples, and then you can ask, okay, how often amongst this sort of samples I drew from the reference is the monotonicity violated? Okay. Mm-hmm. So it's telling you the size of the set on which the map is not monotone. Yeah.
Okay.
Maybe a
Yeah.
quick follow-up question on that.
Yeah.
So if I saw once you had 100% monotonicity. If you don't have 100%, isn't that a problem?
It is a problem, yes. So that would be I mean, I'll get to this. So these are sort of open analytic questions, of which we have many. And that would be the question of okay, so if this map is 94% monotone, and if I had trained one that was 100% monotone, what is the difference in terms of the samples and the quality of the mean and variance and the statistics that I care about, right? That's analytically an open question that I don't know the answer to. Yeah, but I'll talk about it. Yeah, but actually those are good questions. So let me, because I have like, I guess maybe 4 or 5 minutes. Let me now move on to the third part of my talk, which maybe alleviates these concerns, which is, okay, can I just get a monotone, like strictly monotone parameterization? Okay. So again, just the disclaimer here is that this stuff I'm showing you is very experimental. It's just a couple weeks old. Okay. But the answer is yes, you can do that. All right. So the average monotonicity constraint, it has pros and cons. The pro is, first one, most important one, is perhaps convenience. You don't have to do anything special. Just pick, you know, an architecture and just throw in the average monotonicity constraint. It lets you retrofit existing architectures, and you can track how good it is sort of through training. So if you're happy with like 95-6% monotonicity, you can see if you're getting that through your training process. The cons are basically, number one, it's sensitive to your Lagrange multiplier, at least the way we implement it. So it needs fiddling. It could also be violated depending on the problem. So there are cases where you just, no matter what you do, you can't get better than like 80% monotonicity. So that's not good. It's also not theoretically supported, which is what you guys were asking as well. So can you, as I said, can you do strict monotonicity? Yes. So there are 2 ways that you can do it, at least if not more. One, which is what I'll show you today, is using input convex neural networks. So these are neural networks that are convex in their input variables. And there's also a recent paper came out this year in NeurIPS, where they show actually how to construct strictly monotone networks directly. Okay. And the input convex networks, it's actually a very simple idea, very elegant idea. It simply uses these basic facts that non-negative sums of convex functions are convex, and composition of a convex function with a convex non-decreasing function is also convex. So if you pick a neural network, you restrict your weights to be positive, and you pick your activation to be a convex non-decreasing function, you get an convex network. That's the basic idea. It's this paper of Amos, Zhu, and Coulter. All right, so how do we implement this? So again, you have your GAN training. You simply change this class of maps that you're looking at. So they're block triangular maps. Again, this familiar parameterization. You simply take K and S to now be the gradients of 2 input convex networks. So little k is fully input convex. It's a map going from Rn to R. Little s is partially input convex in the sense that it's only convex in its second variable. So S of x as a function from Rn to R is a convex function, okay? And because we know the gradient of monotone maps is, gradient of convex functions is monotone, we get the monotonicity constraint exactly if we use this parameterization. So let me now just quickly in the last couple of minutes just show you that this actually works surprisingly well in sort of a benchmark inverse problem. So we're going to do Darcy flow again, but this time the infinite dimensional version, in the sense that the permeability field A, which would be our Y now, is actually a continuous function on the box. So it lives in a function space. So in that sense, it's infinite dimensional. The measurements are, again, measurements of pressure on a uniform grid. It's a 7 by 7 grid for the numerics I'll show you. And the goal, again, is to recover Y, which would be this permeability field, from an instance of the pressure measurements. And the way we do this is just the details of the numerics. We discretize the PDE on a 64 by 64 grid. We need to put a prior on A. We use a log normal Matern prior. So we write A as the exponential of U, where U is a Matern Gaussian process with this Matern covariance operator. Tau and alpha are parameters. They repeat them to be 2 and 3 for the numerics I'll show you. And delta is the Laplacian with Neumann boundary conditions. Generate 100,000 data points by drawing A and then solving the PDE, generating noisy measurements. We use PCA to reduce the dimension of A to 50. This we've had a lot of success with, generally for training neural networks to work on function spaces. Doing this PCA dimension reduction works surprisingly well. I mean, at least for elliptic PDEs because of their smoothness. And then you parameterize your MGAN using input convex networks. And you train the MGAN basically to condition the PCA coefficients of A on pressure measurements. And this is the result sort of showing you basically, can you solve the inverse problem with this method? So on the left are 3 instances of the true permeability field A. In the middle are the MGAN samples. So these are conditional means. And on the right are the variances. So the conditional means are matching sort of the ground truth permeability, which is the type of result that you like to get in inverse problems to make sure your method is at least capable of solving this problem. There's a lot of comparison to be done here. So how good is it compared to MCMC and so on? Unfortunately, we haven't done that yet. But you know, if you're interested, I'll be happy to keep in touch later. All right, so let me wrap up. I have like 10 seconds. So I showed you a method for model agnostic conditional sampling. You can do probabilistic supervised learning like the MNIST example. You can solve Bayesian inverse problems with it. It takes the measure transport viewpoint towards conditioning. And it has a straightforward implementation if you would like to get away, if you're okay with the average monotonicity constraint. If you're not, you can always do something like the input convex neural nets. Of course, this can't do everything. So when I think you can use MGANs, when it might be helpful, you need large training sets because there's no free lunch. Like if I have 10 training points, I cannot train this, right? Inverse problems that have unknown black box forward maps, or they have intractable likelihoods. Imagine like a stochastic forward model. When not to use this method, obviously, if you have limited amounts of training data, if you have very expensive forward maps, you might have to do some kind of model reduction or emulation first. And also, this is something I didn't get into, but generally, if you have highly concentrated targets, it may not work so well. It's because you're getting to the limit where your target has atoms, and the theory tells you that you cannot construct triangular maps in that case. And lots of open questions in approximation theory. You know, the jump I did going from the ideal theory to the implementation is huge. So there's a lot to do in terms of consistency, getting convergence rates for the target maps and so on. Choice of the architectures, we don't know which one of all these architectures is going to be a better choice. What is a good cost function? We empirically found the GAN seems to work well. Wasserstein GAN, we tried, it wasn't so good. Normalizing flows, they use Kalbach-Liebler. You know, Wasserstein metrics would be more convenient for theory. We don't know really which one is better. And then about inverse problems, there are a lot of sort of applied questions about how really feasible is this method compared to something like MCMC, which is again the gold standard. All right, so let me stop there and thank you all for your attention. You can find the paper on arXiv or you can find it on my website too. Yeah, thanks.
Thank you, Bamdad, for this excellent talk. Wow, it seemed like at the end you have like a 10-year plan now of open questions, of things to solve. I have some questions, of course, but I think I should first let other people ask questions. So yes, let's open up the floor. If you have a question, then feel free to just unmute yourself and ask.
So if I could start, I've got a question. Namely, you talk a lot about the monotonicity of the transport maps between the measures. And obviously that brings to mind optimal transport, where you've got some sort of monotonicity, or where in many cases your optimal transport map is precisely the gradient of a monotone function. Can you explain to me the big differences or the connections between the block triangular and the optimal transport approaches?
Yeah, so this is actually, yeah, so there is a connection. So I guess, okay, about the block triangular maps, I don't know. But about the triangular maps, so for North Rosenblatt in particular, there is a paper, I think, by Stefan Tobak. There might be another author that I can't remember their name, but they basically actually, wait, sorry, my bad. I believe I even have the citation. This paper of Bonnet, actually, yeah. So they actually show that you can get the North Rosenblatt map as the optimal transport map, but it's for a specific cost function, choice of a cost in optimal transport, and in a certain limit. So you basically need to sort of weight your cost function in different coordinates, let's say in Rn, and then you need to take the limit of, I think, those weights going to 0 or something like that, and you can get the KR map. The main issue is that, you know, optimal transport maps typically turn out to be full maps, in the sense that their Jacobians are full matrices. So it's kind of hard to get something that is triangular in that sense, right? So there is a connection, you know, in this paper of Bonnet, but it's not like easy to just set up an optimal transport problem and just get like a triangular map, I think. Yeah.
Makes sense. Thank you.
Are there any other questions?
So I have a quick question. So Bamdad, at the end, I think you said that you found that the Wasserstein GAN, that choice of cost function doesn't work particularly well. I guess that kind of surprised me, because I think, you know, the Wasserstein GAN actually did much better than the previous, than just the regular GAN. Is there sort of a reason why?
I don't know really. I mean, maybe I don't know if Nicola is here, he might maybe give a better answer. I think we just tried it at the beginning and it didn't work as well as just standard GAN. It might have been the way we implemented it. I mean, I'm not claiming that Wasserstein GAN is not good. It might have been the way we implemented it. I don't know exactly. I guess my point here is more like, we don't really know which one is optimal. I know there's like Wasserstein GAN GP, I guess, right, with gradient penalty that seems to be doing very well in recent sort of publications. We haven't tried that. I don't really know. I'm just raising the question. Yeah.
Okay, yeah, that's fair enough. I mean, in the sort of applications, then you tried the Wasserstein GAN, were these high dimensional problems or were they sort of low dimensional?
That's a good question. I don't know if we tried it on MNIST. I know we tried it on the lower dimensional problems. Yeah.
Yeah, I guess I would expect there not to be maybe too much of a difference in lower dimensions.
Yeah.
The high dimensions, I guess, is where, you know, things more likely to be singular, and that's where the Wasserstein GAN might be more effective.
Yeah. I don't know. I mean, I don't have a good sense of these, like which one of these methods is these costs are going to be better, because to be honest, I don't know, you know, we haven't done the theoretical analysis. I don't even really know what are the right tools for doing such an analysis to actually show one is better than the other. All I know is if the standard Wasserstein metrics would lend themselves very nicely to, if you want to do sort of approximation theory and convergence theory, right? And there's something we're working on with Youssef and Ricardo and Nick and also Amir Sagiv. because there's sort of, Amir has theory for connecting map approximations to Wasserstein distances between measures. So in that sense, this is the natural choice. But whether it works practically or is it better than GAN, I don't know.
Can I comment slightly on this?
Yes, please.
So we have tried it, and we've tried, so I've tried it on both high dimensional and low dimensional problems. And also we have tried the GP version as well, all these tricks that people have come up in the literature to train these things. And none of them have worked as well as the standard GAN. I think mainly due to the way it interacts with the average monotone constraint. It seems that that particular loss function, when you slap this Lagrange multiplier for average monotonicity, just the optimization just seems to not work well. We haven't tried them with the input convex neural networks, and that can potentially change things because now you don't have this monotonicity constraint, so the interaction with the optimization might be better there.
Thank you. You saved me.
Yeah, thanks. Another question. I mean, so I guess, okay, so when you introduce these sort of GANs, I mean, you did this in the discrete domain with sort of particles, and eventually these became expectations. I mean, is there any theory on this sort of, discrete to continuum limits?
You mean for GANs or in general?
Yeah, I guess just in general.
So it's on our list of things to, like, it's on this huge list of, many theoretical questions. To me, it seems, so such problems have been looked at, I think, in the empirical process literature. That's pretty much the main goal, is you minimizing a cost function with an empirical approximation, and then you want to know how well or how fast the minimizers converge. So to me, it seems like the tools should be there. Whether or not it's being done for something like GANs, I don't know. Yeah, it's on our list though to do it for this problem.
Yeah. Okay. Yeah. Thanks. They were my questions. So.
Yeah.
Can I ask a follow-on on that one? So what you're constructing in the end is an approximation of samples, right? I mean, it seems that the theory is telling you that it should actually be exact, but then you have this condition of, for example, the monotonicity, which might not actually be completely satisfied when you implement the method. So do you have any idea of the size of the error, or how probably the degree of, how much monotonicity you have in the map that you learned will influence that kind of error?
Yeah, so that goes to the question about what do you mean by these numbers, right? The short answer is I don't know, because and this actually also goes, in my opinion, it goes to some interesting sort of approximation theory questions in the following sense that so if you look at this sort of theorem, you need the surjectivity of T really to hold for all X star in the support of the target. So you don't need this to hold everywhere in the domain in Rn, let's say, right? This only needs to hold in the support of the measure. So then it's the question of, okay, if the map is not monotone in an area where you have small probability mass, how does it actually matter or not? Which to me, it's a question of basically, if you were looking at approximation of your map, let's say in some LP space, what is the measure you need to pick for that LP space, right? Because you don't want to do, LP with respect to Lebesgue, because then you're gonna have huge errors in the tails, right? What you really want is probably something weighted by nu or the reference. We don't know this yet. And then when you do that, then the question becomes again like, okay, having that in mind, how much does this sort of monotonicity matter? I don't think we're weighting these with respect to samples. So this is actually, just computed over the whole space, right? So if this 2% is really in the tails of the measure, maybe it doesn't matter, right? But still, we don't have any kind of rigorous theory for this yet. And I'm not aware of anything similar to, or related to this out there. So, you know, I don't know. I'm just sort of telling you what I've been thinking about. Yeah.
Lots of interesting questions to work on.
Yeah.
Are there any other questions? I mean, it is yeah, go ahead.
So in the experiment at the very end, you have, so it's not a very clever question, but I really want to know. You had 3 columns and one of them is the variance, and you completely skipped over these 3 plots. But I have the impression you wanted to tell us something about this because it's on your slide. So I was wondering, is there something that these 3 things tell us? Because I don't.
Yeah, so I kind of skipped over them because I was looking at my watch, and you know, it's like the train, you know, approaching you from inside the tunnel. So the variances, I guess, I put them here because I wanted to show that you can actually, because when we solve inverse problems, typically in the Bayesian way, as we're doing here, the first thing you do is you look at the mean and the variances, and you kind of expect them to reflect sort of something reasonable about your synthetic solution. So here the mean seems to match sort of your ground truth sort of well. And the variances, you kind of look at them to make sure things are reasonable. So in this case, we have sort of a grid of 7 by 7 grid of points where you're taking measurements and it's uniform. So you would actually expect to see this kind of variance, which is fairly small. They're all like 10 to the negative 6. And you kind of see sort of areas of smaller sort of variance, and that's kind of because you have this uniform grid. You also expect to see higher variances in the corners, which is exactly what we're seeing. But this is just because, you know, if you're familiar with Gaussian process regression, these are the type of things you expect to see because you basically don't have information outside the domain, so your variances go up. So for now, these images are only telling me that things are working as I expect them to. The real test would be to compare these means and variances with MCMC samples, which we haven't done yet because, again, this is like fresh off the oven. And also there's another problem. Maybe I can take this opportunity to like brag a little bit, which is that here we use 100,000 training samples for the MGAN. So your main cost is in solving the PDE 100,000 times. If you wanted to solve the same problem with the MCMC, and if you implemented something like the preconditioned Crank-Nicholson, that can easily take millions of samples. So you have to solve the PDE maybe millions of times to get the same quality, right? So that's also going to take a lot longer to do that comparison as well. But yeah, I mean, at the moment, this just tells me intuitively from my inverse problem experience that the samples we're getting are actually reasonable. Yeah.
Yes.
Okay. Are there any other comments, thoughts, questions? Okay, we already had a very good discussion, going over the hour a little bit. So thank you all for staying with us, and thank you, Bamdad, for this really interesting talk today.